Hello everyone, Kiren Mukkavilli from Qualcomm Wireless Research. Thank you all for this opportunity to share our views on what we call passive MIMO or RIS, or we have been seeing so many different names for these structures here, and I'll get a little bit into why we prefer to call this passive MIMO as a bigger umbrella under which all these other terminologies do come in. So I want to start off quickly with what the starting point is, and it's 5G. And if you just look at how 5G has been doing, it's been phenomenal in terms of its adoption. Just looking at about 300 operators that have already deployed, 300 more operators is coming up, about 1 billion devices already shipped out, close to 5 billion kind of numbers that are projected in the next couple of years, number of designs, and so on and so forth. So this gives us a perfect launch pad if you just look at even the adoption compared to how things moved with LTE at least twice as fast, if not faster. So what we're doing is essentially seeding 5G devices, 5G technology, and 5G design paradigm all around. And take a quick look also at how 5G evolved in itself, even starting with release 15 in 3GPP, and then the first three releases, 15, 16, 17. It's kind of defined what 5G was, laid the foundation, and then the second wave of innovation now coming in, starting at release 18, 19, 20, which is now being termed 5G advanced. Then that'll lead us into 6G, and that's the connection here. And there are two things going on as we look at this evolution. One, even as we look at the first three releases of 5G, laying the foundation, and then the next three releases, along the way, in addition to all these design enhancements that came in, we also started introducing some new elements into the topology. So for example, we have nodes that are now referred to as integrated access and backhaul. Again, one of the key enablers for millimeter wave to get to the kind of density that we need for millimeter wave deployment. And now in release 18, we're talking about what's called network controlled repeater, NCR, or smart repeaters, which I would say is a precursor to RIS or passive MIMO going into 3GPP. So all the elements that are needed for RIS are actually taking shape now as we speak in the form of NCR in 3GPP, and then that will actually pave the way for some of the RIS-related discussions to come up in 3GPP. And along the way, just a quick word also for how 3G evolution is expected to happen. Of course, it's not formalized in 3GPP, but based on all our discussions with all the major players in the industry, this is how it's shaping up. Release 20 in about the year 2025 or so is when the study item for 360 is going to start in 3GPP. All the initial discussions about what technologies should be considered, what's actually going to make a difference compared to 5G, and then in release 21 is where 5G designs will start getting standardized. And even release 19 and 20, the next two releases, we have SA1 trying to talk about the requirements that we should put on any 6G designs. So all of this is also happening in parallel. So, and while we talk about 6G, and I also refer to the new kinds of network nodes that are also getting introduced in 5G, what's also important is that these nodes actually help us with network energy efficiency. And that's going to be one of the key themes of 6G as well. How do we design these networks such that they're sustainable from an environment point of view? And one key component is going to be how do we make sure the network is energy efficient, and how do we get to that using the technology enablers that we have. And you can see a listing here where, of course, you can talk about how it's going to go impact industry, but right now I'll just focus on what's happening or what kind of technologies you can think about from a design point of view. You can start thinking about how to make the waveforms more efficient. How do we make the PAs more efficient? How do we learn to live with distortions in the waveforms? Can that actually help us improve the efficiency? And I know there was some discussion earlier and even some questions asked, do we necessarily have to design these PAs for this wide band? Can we actually get more efficiency if we went after narrow band? Questions like that will actually start to come up in the realm of 6G. And along the way, can we actually do more energy harvesting? And going back to some of the talks earlier in the day, can we start doing some backscatter, energy harvesting based devices? better designs for LNAs and things like that. And then on the network side, can we actually start doing anything with the topology and the network nodes that we have? And passive MIMO RIS is actually going to sit squarely in the domain. That's going to be one of the key components that will actually get us there. So if you look at starting with the baseline, the basis that 5G has set up, how 6G is going to look like as 6G network and deployment. It's going to be a collection of a whole lot of nodes, again, depending on what the environment is and where the fiber ends and where we have to go wireless and how do we still get to good coverage, covering all the bands. We're right now talking about FR1 and FR2 and FR3. Yesterday, John referred to that in his talk, and earlier today there was also a reference to that in Samsung's talk, whether it's, we call it Giga MIMO or X MIMO. It's in the FR3 band, which is 7 to 16 gigahertz is what we think is going to be of interest over there. So we'll start seeing characteristics like millimeter wave, but hopefully it's going to be more like FR1, where we'll get all the wide coverage, but also large bandwidth of FR2, that we'll be able to design this FR3 networks for 6G. But then towards that, how do we still take care of the densification that's needed and without expending too much of energy or cost? And over there, as you start looking at the collection of nodes that we're going to have, whether it's small cells, remote radio heads, or network control repeaters that are coming up, or intelligent surfaces, and even the intelligence at that point, as we just saw, is the intelligence residing on the network, or is the intelligence within these nodes that we go deploy? So there are going to be all kinds of these questions, and also all kinds of the designs that will come up, and we'll be able to pick and choose depending on the specific concerns that we'll have to address as part of the deployment. So as part of this, and if you talk about passive MIMO, which is also being referred to as RIS, as I said, so what exactly is this? And at a high level, and I'm not going to get into details, we have had several talks already talking about what exactly is expected of this passive MIMO RIS nodes. At a high level, essentially what we are saying is we want to be able to control the reflectivity or the directions in which the beams go out after they get impinged on these devices. That's just one of the properties. There are so many other properties that we can also start playing with, including polarization and so on and so forth. But for a moment, if we just focus on the reflection aspect of it. So if we assume, okay, these are the nodes that will help us control that, and that could be done in a passive fashion, as we just saw in the previous talk, or we can actually start putting in some intelligence there where we're able to now control exactly the direction in which the beam goes out. If that's the case, so what can we get out of these nodes? The first thing is we can address some of the coverage challenges, especially some of the difficult scenarios. And what are the difficult scenarios that we can think of in cellular networks? Cell edge, where you just don't have enough power to extend the network, and at that point, you're forced to put in a small cell, forced to put in a repeater, or hopefully this is going to be a low cost, low power, low weight kind of a deployment, easy to deploy, that you can put some of these nodes and it actually ends up extending our coverage. Or you could actually have scenarios where you have blockages, and now you have to get around the blockage, and you may not be able to afford to put in new nodes just to get around this blockage, because it's also going to introduce interference and end up distorting the entire coverage planning that was done around that region. And apart from that, once you have these nodes, you can actually start thinking of other functionalities that you can bring in. Positioning, for example. Now, you're going to have nodes that you insert in the network whose locations are known, and these are going to be your new reference points that you can make measurements from and also start bringing up better positioning out of this. So a lot of exciting functionality that you can actually build on top of this. If this is the case, then I guess there are two questions that will come up. Okay, how are we doing with respect to the research that's going on here? And we have seen in quite a few talks here today, which have built this reflector surface and made some measurements. But how is the industry looking at this? And how are standards bodies looking at this? So quite a bit of activity around that as well, and I've listed a couple here. There's one that's going on with ETSI. There's something called an industry specification group that ETSI has established, let's say about 30 members out there. So there, it's been quite active, almost on a monthly basis where the group meets. But the questions that are being asked here are, in some sense, very fundamental. Okay, what exactly are these passive MIMO nodes or RIS nodes going to be able to do? What kind of use cases can be mapped to this? What kind of KPI should be defined? What is the channel model going to be with these nodes in there? And finally, what is the path forward to standards? So that's the kind of questions that's getting discussed there. In China, there's another alliance that's come together, RIS Tech Alliance or RISTA. Again, quite a bit of involvement from academia and industry over there. Also, more or less answering similar kinds of questions about the use cases and design and complexity and so on and so forth. And the last row there is about some of the trials and especially among operators and vendors that's happened, covering both millimeter wave as well as FR1, the 3.5 gigahertz. And I know a lot of the talks today actually addressed millimeter wave bands because that's where the size of the area also becomes somewhat justifiable. And also, you do run into blockage kind of issues over there. But we do actually see quite a bit of application in 3.5 gigahertz, and especially as we go into 6G realm, once you start talking about 13 gigahertz kind of frequency bands, it actually becomes more and more relevant as well. I'll show you some numbers for how it's going to look like in 13 gigahertz. So quite a bit of activity. Everything is gearing up for release 19, release 20 kind of discussions and specifications in 3GPP as well. So having said all of this, okay, how are we doing on performance? Where exactly does this passive MIMO node help out? And what we're showing here is actually a first order analysis just for us to understand, okay, how exactly it's working out and where can we expect to see some gains out of this. So what you see is, let me try to use the pointer here. So there's a base station here, which is set up at at the origin, and then it's a 25-meter tall base station, or it's sitting on a building which is 25 meters tall. And then the UE is sitting somewhere here, and we are varying the location of the UE, the distance of the UE from the base station. And there are two paths for the signal to take, or two scenarios that we consider here. One, where the UE can receive the signal directly from the base station, or the base station can make use of the path going through the passive MIMO node to the UE. So now here you have to worry about two links, the link from the base station to the passive MIMO node, and then from the passive MIMO node to the UE. So now, intuitively, you can see that this link here, or the combination of the links, will start making sense only if the gain that you get out of this passive MIMO node is able to compensate for the additional attenuation that you have, or the path loss that you have, going through this composite channel, the two links that you have. So if it's, and we have some curves here just to show, okay, what kind of distances then start to make sense. One key factor that comes in here, and that's not been modeled here, is what kind of blockage are we going to experience here? If it's just line of sight for all these channels, then there's no way this RIS is going to help out, just given the additional path loss that you're going to encounter. Once this becomes non-line of sight, then you start to stand a chance. And more important thing is when you start having blockages. And here's some sample numbers where at 13 gigahertz, for example, if your base station is about 500 meters away from the UE, and you start looking at different distances of the UE from the RIS, you're looking at 50 to 60 dB that you have to make up in terms of the path loss difference. So now how much of this for the blocker, and then the rest of it for the gain that you have to get from the RIS? And that's one of the questions that was asked earlier. How big does this RIS have to be? And this is the answer to that. The size of the RIS will depend on the deployment scenario and how much of path loss attenuation difference that you're trying to fight here. 3 minutes, okay, good. So the other question that comes up is, so now when we're looking at RIS, and even from the previous slide and even over here, you can see that most of the gains actually start to come up when you are actually very close to the RIS. You're talking about 10 to 20 meters where you start seeing this large improvement in spectral efficiencies. But then on the other hand, if you look at the size of the risk and are you in the near field of the risk or the far field of the risk, it turns out that if you start talking about this kind of distances for large risk surfaces, then you are actually more likely than not in the near field of this risk. And if that's the case, what does it mean for the channel modeling that we've been using? So do we have to come up with new channel models, and how does the coupling between these elements behave? And a lot of those fundamental questions start to come up. And these are also the questions now that we need to start answering. Are we even doing the modeling right? Even the numbers that we are showing, do they still hold up once we start taking the near field into effect? So having said that, this is going to be my concluding slide here, just to point out what kind of opportunities and challenges we have now around this risk. So as I said, with release 18, with this introduction of network controlled repeater, quite a bit of foundation has already been laid, where now there is actually a framework where the G node B can actually tell these nodes what kind of configuration it's operating in, if it's TDD, up-down configurations, symbol boundaries, and control channel. I know there was discussion about the complexity associated with decoding this control channel, but those elements have been put in place. But then once you start bringing in risk, there are new challenges that we still have to address. And some of those are how do we actually now start getting the channel estimates? What is the CSI mechanism? How do we figure out the beams, the complexity around it, the power consumption, and so on and so forth. And then finally, on the technology front of it, how do we build these surfaces to be low cost, low power? And the success of RIS is going to depend on how easily we'll be able to deploy these nodes. And if we still have to go look for cell towers or cell tower kind of deployments, it's going to pretty much make it moot. So we have to make it easy to deploy. So having said that, so this is a slide that John showed yesterday in terms of all the technology enablers for 6G, and we do think that as part of the air interface innovations, doing a good job on RIS is going to be very, very important to get 6G going. Thank you. Okay.
Hi. So my question is, we always talk about these RIS at millimeter waves. Do you think we will need them, or we will use them at 3.5 or 5 gigahertz?
So 3.5, we've been investigating that, and I guess there are two ways to look at this. One, is there going to be a need to use this? Can it actually serve a purpose which is not being served by other nodes? Probably the answer is not going to be as much, and also the size is going to be a huge factor there, just given the wavelength. And to be able to get a meaningful number of elements into this RIS array, it's going to be maybe a little too large and too heavy to be able to get any gain out of it.
At 3.5, you can just roll it, you know, it's so low cost, you can just roll a polyamide thing and attach little diodes to it, or attach something.
Yeah. So hopefully if we can get the technology where we can just roll it and make it so light that hopefully maybe at some point just paint this on building surfaces and get that going. So,
but basically you say we most probably will know. How about 5 gigahertz?
5, maybe that's a point where you can start considering, but you're thinking 10 to 13 gigahertz, where that's going to be a new spectrum, hopefully for 6G. And over there, we think it's going to be very, very beneficial.
And the second thing that nobody is talking about is that, assuming they are intelligent, intelligent from the word that they are reprogrammable, not intelligent that, you know, you are intelligent and you know how to design them to make a special beam, but that the beam is, you know, is changing. But the RIS doesn't have any intelligence itself. How does it know where to point to the user? You know, it has to track the cell phone and maybe change its beam from a flood beam to a narrow beam and so on.
Yeah. So you see, you're right, and especially as we keep increasing the number of elements in these surfaces, that becomes a bigger problem, because how much of control are you able to carry, and how quickly are you able to now change?
Yes.
Because the switching time and what's actually happening to the surface while you're switching, is it in a it may be okay if it's an unusable state, but is it actually distorting the signal in some form that it's actually even interfering with the network operation? That's the other question that comes up. And we're looking into some designs where you're not necessarily changing the phase of every single element, but hopefully changing them in some groups so that you can minimize the overhead. But right now, the assumption is that it's still carried mostly with the base station, and you're finding a way to get it out to the RIS surface, because otherwise now you'll have to start carrying more and more computation complexity at the RIS node, and that starts to look more like the small cell itself.
But then the RIS must have a communication channel to the base station, maybe just one antenna receiver, low data rate or whatever, so that it can get commands like go there, or do things.
That's right, yeah. So that's the framework that we have now with what's called NCR in release 18, network controlled repeater, where it's going to be a over-the-air, very lightweight control channel that goes out only to this node. Other nodes are not going to look into that, but this node, without explaining too much of complexity, will be able to decode, figure out what if the weights are preloaded, then it just at least figures out which one to pick and stays in sync with the G node B. So it has a communication channel with the G node B.
Thank you.
Thank you. Okay, thank you. There's okay.
So
I thought I got.
So I think Gabriel asked my question. Thanks for the presentation. My question was more on the system level, right? You need a feedback loop to be able to tell where to steer, right? So at least even if it's intelligence lies in base station, the user is moving. So looks like you answered that question. But the second one is it's not quite linear. Even higher frequencies, the propagation is becomes complex, right? There's reflections, and you don't have always like a line of sight type, even for reflected wave. Has there been any studies? Is it really as efficient as we think it is? Basically, there's multipath. There's also multipath even for millimeter waves, right?
Mm-hmm.
So to go around it, it's not very simple. It's not very like linear that, hey, user is moving 10 degrees to the left, you follow it. Has there been work in like in models?
Yeah, so we've been modeling this at a system level and also been doing some field studies, but the answer to your question still comes down to the deployment scenarios. So first of all, you'll have to deploy these RIS surfaces at a point where they can clearly see the G node B. So some kind of line of sight between the G node B and RIS. And from RIS, at that point onwards, it's probably still going to be limited in terms of the view. You may not be able to cover every single point that was otherwise blocked by G node B. So maybe that means that you may have to deploy multiple RIS surfaces so that you get more extensive coverage. But the hope is that we're going to make it low cost, low weight, low power, and all of that. With all those boxes checked off, then you'll be able to deploy enough of this.
Thank you.
Thank you. Thank you. Thanks, everyone.